So in today's video, let's talk about a visual explanation of how an AI system might learn the joint probability distribution by decomposing it into a product of conditional probabilities. P of x1 represents the probability distribution of the first variable x1. So in this case, it follows a normal distribution which is centered around 0, and the second plot shows the conditional probability x2 given by x1. So here x2 is normally distributed around a value which is influenced by x1. So for its simplicity, this is shown as a normal distribution which is centered around 1 given by x1. The third plot represents the conditional probability of x3, which is given by both x1 and x2. So this distribution is more tightly centered around a value, which is influenced by both x1 and x2, which reflecting higher certainty when more information is known, right? And the final plot, joint probability distribution, which is P of x1, x2, and x3. So this joint distribution is obtained by multiplying the individual conditional probabilities according to the product rule. So this final distribution represents the combined probability over the sequence of the variables, which normalized to ensure it form a valid probability distribution. In some generative models, like DeepMind's WaveNet, once the joint distribution is learned, new data can be generated by the sequentially sampling from each conditional distribution. For example, we sample x1 from P of x1, and then we use the value of x1 sampled in the previous step to sample x2, and then we use the sampled value of x1 and x2 to sample x3. So this approach is very powerful for generating complex sequences like audio, where each part of sequence depends on the previous ones. So this decomposition into conditional probabilities allows us the model to be captured intricate dependencies within the data, which enabling it to produce highly realistic samples. Let's look at the first plot, which is the learned distribution P of x1. So this is the distribution of the first variable x1, which is the model learns directly, and it is a standard Gaussian distribution which representing the prior knowledge or initial distribution of x1. In the second plot, these curves represent the learned conditional distribution of x2 by given specific values of x1. For example, the distribution of x2 when x1 is equals negative 1.8 is shown as one of the colored curves. So this model learns how the x2 depends on x1. In this simplified case, the mean of x2 shifts depending on x1, which illustrating the dependency between these two variables. The third plot shows how the model learns the conditional distribution of x3 given both x1 and x2. For example, the distribution of x3 when x1 is equals negative 1.8 and x2 is also equals negative 1.8 is depicted by one of the curves. So this step highlights how the model builds increasingly, and this complex relationship between the two variables learns how each new variable's dependence on all the previous ones. So how can this model use this information? Once the model has learned these conditional probabilities, it can generate new data by sampling sequentially. So first, it sample x1 from P of x1, and then, given the sampled x1, we can sample x2, and then, given the sampled x1 and x2, we can sample x3. So this process can continue for more variables, which result in generating a sequence that reflects the learned joint distribution.